So this is lecture number 3, and yesterday we have seen some steady states on a type 1 PLL, basic settling or basic phase error which you will have when it locks to the frequency. So today we are going to see a large scale functioning of the PLL. How does it acquire lock? How does it generate voltage and all? Okay. So we start with so this will be the means from now till we completed the acquisition of PLL is what we are going to study. Okay. So we saw that a simple type 1 PLL is this has a loop filter and a VCO. Okay. The input and output signals are still voltage signal, but what we are ensuring is the phase and frequency. The output of the phase error detector, which is a mixer here, is VE. The output of the loop filter is V control, or we can just say VC. Okay. And to begin with, let's say the free running frequency. So we define couple of things. The input frequency is equals to omega n, and free running output frequency is omega free. Let me just write it in that way, or use a better, easier denomination, that omega 0. Okay. Now we have seen that the multiplier is acting as a phase error detector, and we are using a simple first order low pass filter as a loop filter. Okay. And the VCO is a voltage control frequency source, where the output of the VCO is dependent on V control, VC, and this is the connection which we have here. So let me ask the question, if let's say omega n is greater than omega 0 at t equals to 0, and your VC of 0 is equals to 0, right? So how will it start building up the voltage which it requires such that it locks to the desired frequency? And what we know is that in steady state, and this is from yesterday's lecture, in a steady state, your omega n is equals to omega 0 plus k VCO times VC, which is a DC voltage here. And the DC voltage VC is also equals to the, because this low pass filter is also equals to the average output of the phase error detector. But to begin with, it was 0. Okay. So let's see how does it acquire the lock. Before that, let's consider part by part. Let's say this connection is not there, and it is not connected to the VCO. At that time, what is your V error? V error is, let's assume that A in and A out, I will just say they are equals to this one is omega in plus omega free or omega 0 times t plus some phi offset, or so this one is integral of k VCO times VC dt, okay, plus sine of omega in minus omega 0 t minus k VCO VC dt. This is the equation which we yesterday worked out for the phase error detector. Okay, so when I am saying that this loop is broken for open loop, okay, VE is only equals to, if A in and A out are both equals to 1, let's consider that this particular thing is going to be filtered by the loop filter. So we are only considering the low frequency signal is equals to sine of delta omega t and Vc was 0, so this was the only this was present at the output of the phase error detector. So if we consider only the phase error, that is equals to delta omega times t. Okay, so this is the rate at which the phase error would be increasing all the time if this was an open loop. So let me just plot that. So let's say, so if this is my time axis, okay, so this can be arbitrary. So this is minus 2 pi, minus pi, 0, pi, 2 pi, and this is phi error in open loop. And all these instants are actually your, they are periodic with delta omega. This is how the phase would be increasing, and the output of the phase error detector will be sinusoidal. Okay, so if that particular thing is sinusoidal, so we have, let me just, okay. So this is just, I mean, it's not turned out to be a good sine wave, but let me just say this is a, okay, oh, this is going crazy. So let me, so this is your VE, which is at the output of the loop filter, VE of T. Okay, now in case we give this VE, for example, let's say there is a replica of this oscillator, okay, and we just, this is not still connecting the feedback loop, we control this oscillator output. What can you comment on the frequency of the new oscillator? So let me just say omega 0 dash. So the control voltage which you are feeding is a sinusoidal control voltage which is having an average of 0, which controls the output frequency. So overall there will not be, on an average there is no change in the frequency. Okay, but now since we close the loop, then see what happens. So let me just write it here, that PE of t is delta omega times t minus k VCO times VC dt. So right now, as first assume that the VC which I am considering remains constant for the period I will show here, right? But this, when you close the loop, everything happens simultaneously. So for now, let me just say KVCO times KPD, whatever the phase error detector gain, times your phase error. And in this case, phase error is sine of phi ET times dt, and I'm considering this phase error for open loop case. So let's say when you have the open loop, means when you're considering the phase error for the open loop, how does it change the resultant phase error? So did you get the idea that what I show you before is if you do not have the loop closed, your phase error changes sinusoidally. Now I use that sinusoidal phase error to control the control voltage of the VCO and thereby the frequency. For just the analysis part, I am saying just let's assume that the sine phi e is constant for our analysis. Okay. So now, what can you say during this period of the? So you see, sine of your VET is actually nothing but this, right? So during this period, how does your phase error will change on the on this curve? So let's say, well, this will not be okay. So what I'm asking is, earlier when you were having only a linear rate, the phase error was changing by delta omega slope, right, with respect to t. Now when you are having a something another thing which is subtracting from that phase, and the time when it is positive, the phase error which you are going to accumulate will not be with the same slope. And for the reason when your for the region when your sine phi is positive, it will surely be lesser than the time which you expected to get the phase phi, to accumulate the phase phi. Okay, so this phase will actually come to pi at a different instant of time, right? Similarly, means it reaches 2 pi at another instant. Okay, so this is the new phase error which you can say phi e in closed loop. Okay, so now this phi error acts as a acts as an argument of the control voltage which is fed in the closed loop form. So for that, if I see that, okay, now if this is the new time instant where the phase error becomes pi, then I will have something. This will not be surely a sinusoidal. This will be something. It comes to 0 at a different instant of time, and like this. Okay, yeah. Where? No. So what I am saying is it is basically accumulate a phase 2 pi, right? Now whether it intersects at 2 pi here or not, that's again the will tell you the final dynamics of the system. Here I have just shown you that this will go to 2 pi here, so you can. So what will be the value? Okay, this is again what will be the value of phi e. So if you work this out, this is delta omega t minus, let me just say this value with KVCO is something k, right? You have minus cosine of phi e. Just a minute, this is sine. So you need to integrate it with respect to time dt. Okay, and this is a sinusoidal. So you will see when it has a 0 and 2 pi. Okay, at that time it will be matching 0 to like pi to 2 pi difference. So we can work this out. So this one is, this will become more complex thing because I am assuming that phi is just a minute. So sine, okay. So you have this delta omega t minus k, and this is VE of t. VE of t is sinusoidal with this frequency. So delta omega t, okay, which is minus k by delta omega cosine of delta omega t, and you consider this over one period. Okay, so one period is, you can say t equals to 0. This is normal, t equals to 0 to t, and then you will find this will settle to the same value, right? You got that thing, right? So if you see the, now what can you comment on the average of this new B error? Mathematically you can always prove it, but from just from an intuitive level, this has now no more a sine wave to begin with, and this is for a larger part, it is actually a positive thing, and the other one is negative part is lesser. What is the gut feeling here that what will be the average voltage which comes out? Positive. So let me just say, if the average of this, sorry, the new average voltage which will pass through the filter is some, let's say, VP or VE average, right? Now this VE average develops as a DC voltage which will now bring the frequency of the oscillator closer to the input frequency. So this is how it is going to pull up. Means I will use the word pull up in more like define it exactly, but this is the voltage which it will develop to get the oscillator closer. Now you can do this exercise iteratively and say, now this is the voltage. Now assume that the phase error, now the delta omega has reduced. Now I again do this for this one particular period and get what's the final voltage. Okay, so this is how, yeah. We will come to that. So the thing is, whether PLL locks to that period is a question. It may lock, it may not lock. Okay, and that actually defines the different kind of ranges for the PLL. Whether it will always lock to between 0 to 2 pi, right? It's not at all necessary that, okay, the first thing is whether it will reach. So here there are assumptions which I am taking is that the delta omega which I am considering for the sinusoidal thing, right? I'm keeping that fixed for that period. For that period, this will happen. But this is all a simultaneous process. Okay, now whether within this period it will, because if you see this, the way I have drawn, right, that means that I will always do something kind of this if what I am showing is valid, right? That means the average voltage which you have generated in one single period remains the same whether you go to a 2 pi or 10 pi, right? So the thing is whether that voltage is large enough to correct for the frequency error or not. So there we define whether that if that voltage is large enough, then you lock in. If that voltage is not large enough, then you do not lock in this particular PLL. Okay, so let's say if so the whole idea behind this is to tell you how you acquire that voltage. Means you get a phase error which is average phase error which is non-sinusoidal, which develops an average DC voltage. And if that DC voltage is large enough for the oscillator to lock to a frequency, then good. In this particular, and if it doesn't, then what happens? You will see that. Okay, so where were we? So we started with some frequency error, so phase error, which was delta omega times t minus kvco kpd times ve dt. Oh, so let me just say kvco times vc dt. Okay. Now, this is again the analysis that you have seen before. If you are locked if you are locked to a certain frequency, then your frequency error will not change with time in the lock case. That is, the d phi by dt will go to 0, which implies that your delta omega minus k VCO times whatever average voltage you have generated should be equals to 0. And this is the same as delta omega times, delta omega equals to, this is minus kvco kpd and the average voltage which you have generated at the phase error detector, which is here some value phi e, let me just say phi e average, because phase error output is sin phi. That's coming as a nonlinear gain in a system. So we have that sine of phi e average is equals to delta omega by k. Here k is equals to kvco times kpd. This we saw yesterday also, that if since sine phi e is less than equals to 1, which implies your delta omega by k is less than 1. You cannot generate a voltage, means other than this gain factor, with this kind of phase error detector for any delta omega frequency difference. Okay. So means normally if I come and ask that I have let's say for example I have delta omega where there is no limit on the frequency error to begin at the time t equals to 0. So let me just say that if at t equals to 0, omega in minus omega out, omega 0, which is delta omega, there is no limit on delta omega, it's upper bounded by infinite. Okay. Then if the VCO is the only block and the only control is V control, VC, and you have this V out, and the frequency relation is, as you say, that omega out is equals to omega 0 plus kvco times vc, right? So for this particular thing, the only thing which I need to ensure is that vc should be equals to delta omega by kvco in a steady state. Nothing else matters, and this should be a dc voltage if it is locked in the frequency, right? Now if this itself is limited, because I am not able to generate enough VC because the phase error gain is coming as sine phi e, which has a limit on the upper value, then I cannot generate a control voltage for any frequency error. But within this range, within the range delta omega by k is less than 1, I will generate a certain phase offset such that that leads to a control voltage blocking the frequency. Okay. Any questions for that? So the next question is, means okay, this is a very large scale picture and everything happens simultaneously. You generate a voltage, but now let me ask this thing, that I have sine of phi e is equals to delta omega by k in locking condition. Now whether, so you know that sine phi e is also equals to sine pi minus phi e. It's just a mathematical equation. So where does it lock to? Does it lock to phi e or does it lock to pi minus phi e? It can lock only to one phase. So for that, now consider where, at which point this will be stable at all. So coming back to the phase error equation, phi e of t is delta omega t minus kvco times k pd times sine of phase error in steady state. So let me just put it average times dt. This is what we have. And in lot condition, we told that the phase error should not increase. So let me just write it first as k times sine of average phase error in the locked state. So this is phi e dot, or let me just write it as a derivative. Okay, so phi e derivative is equals to k times K minus sine average of phase error. Okay, so we know that d phi e by dt should go to 0 in a stable lock condition, and this is the means this one is the what the phi error derivative of the phi error it is at any for any given phase error. So just plot this when it goes to, I think we all know when it goes to 0, but see where it will settle actually. So let me just plot this as phi e dash by k. Okay, and so let's say okay. So sine phi is positive, then you have the negative, and then you add up to the delta. So this one will, so just for here, this is sine phi e. The negative of sine phi e is this, right? And I added to a delta omega by k. So this particular thing becomes something kind of this. So the x's are just a little bit off. So let me just make this as an axis. Okay. Now what we said that this should be equals to 0. Now you see that this is with respect to phi e average. Now this one and this error is delta omega by k. Shift is by delta omega by k. Okay. So now you have multiple nulls. One here, here, and the other ones are this. This is what I was saying that you can have the nulls at multiple phi e. This is within a pi, right? So just for a, I can just say this one is okay. This is not to the scale, but I think you got the picture. Okay. So now the thing is within this 0 to pi, you have two particular values where you can lock to. Now which one is a stable null, which one is an unstable null? So let me just call this one as null 1 and the other one as null 2. Okay. So now you see if at null 1, black only, at null 1, if your phi e dash by k is greater than 0, right? So if the phi dash by k means the rate at which the phase error change phase error is d phi e is greater than 0 at this point somewhere here, right? That means that the phase error should increase. It's a positive positive rate of phase change. If phase error increases, you are coming in this direction. So whereas when you are in the negative direction, when you are somewhere here, your phase error actually d phi e by dt is negative. Your phase error will decrease with time. You will approach this direction. So from both the sides, if this is a stable null, right, that means if you make any disturbance on either side, you should again approach the same point. Whereas at null 2, if phi dash by k is greater than 0, right, you will move outward. And for this side, you will move this way, right? So this is k is less than 0, sorry, in the same greater than 0, at that point your phi e reduces. So this is like it will surely come in this way and finally settle to this, because once it reaches that, that's a stable point. So what basically inferences can you make from this stability is that at every 0 to 2 pi, means if this is the case, like delta omega means you still have a point where it crosses zero, right? You still like have a stable settling, no matter where you start with the initial phase errors, stable settling for phase error, let's say between 0 to 2 pi. You find a stable point for as till the time delta omega by k is less than 1. Even if, let's say, that's what the thing is, if you start at this point, the red one, then you will settle to a closer null. If you start somewhere away, you will settle to the next null. But you always settle to a within the 0 to 2 pi phase. Okay. So now, if this on the same picture, if I just say that if delta omega by k is greater than 1, then what you will see I'm just plotting it simply like this. Let's say this is for the case delta omega by k greater than 1. So do you see at any point this d phi e by dt goes to 0? No. You do not have any stable null point for this particular PLL or phase error detector, which uses this kind of phase error detector and loop filter. Okay. Yeah. Pardon? So the red one is a stable point. It is enabling. Yeah. No. So the thing is, let's say you are. So what we have seen the before is that I can have the same sine phi e and sine pi minus phi. That's just the equation, right? Now we say where does it settle to? So it can have within a 0 to pi here. Within the 0 to 2 pi, you can have a 2 points where your sine of e gives you delta omega by k, right? Now the thing is, which point is a stable point? So in a steady state, let's say if it is the red point, right, the red null, at that point if you make any disturbance, that is means if your delta omega by k is greater than 1, then the loop dynamics, because d phi e by dt is greater than 0, then phi increases, it comes back to the null. Okay, that's why it is a stable one. Whereas the blue one, if you settle at there, let's say somehow you settle at there, but if any disturbance appears at that particular null, then you move away from that null, you go and settle to the next one. Negative feedback will ensure that it settles to that. Means provided it's not that. So there is one thing, if you are having noise in the system, then it will, if it is settled, it will settle in a stable manner. And because the equation which we use just sine phi, that doesn't tell the stability part. Okay. So this particular thing tells you about the stability and also tells if your delta omega by k is greater than 1, you do not have any null to, just another way of demonstrating. Okay. So now so you have seen that there is certain range of frequencies which it can lock to, and which is locked to means well, even when there is an initial frequency error, then also it locks to, and if it locks to, then it is a stable equilibrium. If you change anything, it will come back to a stable equilibrium with that error. So all these things are categorized in different metrics. So let me just say uh, range metrics for PLL. for PLL. Okay. So the first one is, we will define all these things because this will be defined for other PLLs also. So first one is called as a hold in range, which is defined as the range of frequencies to which the PLL can hold in lock condition, in a steady state condition. Okay, the final settle. So range of frequencies range of input frequencies which PLL can stay in lock. PLL can stay in lock or PLL can hold in. Okay. Now let me, just for this PLL type 1, we saw that, for example I will show here, for type 1 PLL. So everyone remember this is a type 1 PLL, right? So for type 1 PLL, we have delta omega is KVCO times V control average value, and which is equals to KVCO times KPD. This is all in steady state. V KPD times sine of, because the loop filter gain DC gain is 1. So let me just write that also here, KVCO times VC, which is equals to your loop filter gain at DC times your V error average, which in turn is equals to KVCO times KPD times loop filter gain 0 times sine of V average. Okay. So for no matter how you get this voltage, if it can maintain that voltage in the steady state, the PLL can hold in lock. Why I am making a distinction whether no matter where you get the voltage, you will see there are other ranges which are defined in that manner. So here, till the frequency range delta omega by k less than 1, I can always have a voltage somehow such that I can hold the PLL in lock. So the hold in range for type 1 PLL is, in this architecture, is is equal to K. Yeah. Okay. Now the second range is defined as lock-in range, which is range of frequencies which PLL can lock without cycle slipping. Can lock without cycle slipping. So let's see what is cycle slipping. Okay. Cycle slipping is defined as normally that is defined as that you basically your phase error exceeds 2 pi accumulation. When phase error accumulation exceeds 2 pi, means 0 to 2 pi, it's not like minus 2 pi. That's why phase error accumulation exceeds 2 pi. So just look at this example, that the one where I have shown you in this case, right, where I say that in this particular PLL, you are always having this as a periodic, the one, this is appearing a periodic, right? So if it gets the VP, whatever the voltage it needs for the DC voltage for locking in, it should be able to get in one cycle. Okay, if it doesn't get in one, it will not get ever in this case. So from time instant t equals to 0, when it starts locking in, If the delta omega is within a certain range, it will develop that control voltage in one cycle where the phase error accumulates to 2 pi. Got the idea? So thing is, you start at time t equals to 0, there is certain delta omega to begin with, you will start developing that control voltage, and before the phase error accumulates to 2 pi, you develop that DC control voltage which is required for the locking in of the PLL. In this case, let's say if delta omega by k is greater than 1, then you cannot develop that voltage, right? So you are not yet locked in, still you are exceeding the phase error 2 pi. So that is called cycle slipping when you exceed the 2 pi phase error. So for type 1 PLL, what can you say is the lock-in range? So as I explained, for type 1 PLL, what should be the lock-in range as such? Yeah. So because we are considering the whole large scale picture here. So you start up at time t equals to 0 and see where it locks in. Okay. So what can you comment on the lock-in range? That I should get the frequency lock before I accumulate the error 2 pi. Did you get that? And I have shown you for all the frequencies delta omega by k less than 1, this will be the case. Now can you say what is the lock-in range? And this should be, pardon? Omega, no, we are considering the range. Why is it omega naught comes there? The difference. So omega h was the frequency wherever it can lock in, right? That is omega h turns out to be your k, right? But here the thing is, since delta omega by k is less than 1, then as per all our error and the VCO equation, we are able to develop that control voltage within one cycle. Because we have seen even in the stability that within the 0 to 2 pi you lock in. So lock-in range of this particular PLL is also equal to, k in this case. Did you get the lock-in range as such from the concept that the phase error should not exceed 2 pi, and from whatever analysis we have seen before? Okay. The next one is defined as pull-in range. That is defined as range of frequencies. These are all input frequencies. Range of input frequencies. Let me not. Which PLL locks with and without with cycle slipping. So it is not easy to understand this particular thing with this PLL type 1 architecture, because here if it locks within one cycle where the phase error accumulates to 2 pi, otherwise it doesn't lock at all. Now there will be kind of PLLs where you accumulate a phase error 2 pi, you have not developed you have not yet developed the voltage, you again develop more voltage. So it's like you keep on developing or let me just put it, you keep on integrating the voltage in every cycle, such that in the end you develop the required voltage for the frequency locking. So as you accumulate an error more than 2 pi, there is a cycle slipping, but you are still in the end you are able to bring the control voltage large enough to lock the frequency. So that range is called as a pull-in range. That you pull the PLL from wherever it means at time t equals 0, it can be any frequency, any offset or something, but in the end it pulls in. But here in this case, You, if you are only between delta omega by k is less than 1, then only you can lock in, and that you actually lock in without cycle slipping. If you slip the cycle, even then if you slip the cycle, you will not be able to lock in at all. There's no, it's like cycle slipping in this case doesn't help you to increase the control voltage. Okay, so in this case also your omega pull in is equals to k. Pardon? Yeah, so this is the very particular nature of type 1 PLL. Yeah. So whether that is a property of an accumulation or there is some other thing. So what you are saying is I have a PFD which detects the phase error, but the thing which is applied to the VCO always keeps on increasing till it locks. So I will just take the word from statement that the phase error, PFD detects the phase error, but phase error keeps on accumulating till you lock in. So what will you call that phase error keeps on accumulating? Integrator. As soon as you have another integrator, it is no more a type 1 PLL. So that is one reason why you go for a type 2 PLL. Okay. So type 2 PLL can have a larger lock-in range compared to type 1 PLL, even when it is using a mixer type of phase error detector. So you distinguish between the two. This may not be the problem of the phase error detector. This is to do with the loop, whether you are integrating the phase error large enough. Okay. In general, you have delta omega h is always greater than delta omega p, and this is delta omega L. Means lock-in range is smaller because you constrain that you should not cycle slip. Pull-in range is larger than lock-in range because you can cycle slip and generate that voltage. Hold-on ranges, maybe pull-in is not able to do it because of the loop dynamics. But if somehow I give the right control voltage to start up, it will remain in lock. Okay. So this kind of concludes your type 1 PLL and the problems with the type 1 PLL. We will move on to type 2 PLL next. Any questions on this? Hmm. So okay, so the thing is that